Okay. The first chapter, as I said, is about linear systems, system of linear equations and matrices. Here, first we should know what's a linear equation. A linear system is a combination of some linear equations. If you have more than one linear equation and you want to solve them together, and it's called a linear system. First, you should know what's a linear equation. For a linear equation, if the exponent of all variables is 1, okay, here the exponent of this variable is 1. I mean the power, okay? The power of all variables must be 1. As you see, a1x1 plus a2x2 plus up to anxn. Even if we have ax plus by plus cz equals, let's say, d. This is a linear equation. This is a linear equation. As you see, the exponent of all variables, and our variables are x, y, and z. Okay? The exponent of these variables are all 1. Okay? This is a linear equation. And this one is the general form of a linear equation. Here, x1, x2, up to xn are called variables. These are the variables. And a1, a2, up to an, these are the coefficients. Okay? As you see, a1 up to n are real numbers, are called coefficients, and x1 up to xn are the variables. And here, the constant term in the equation is b. It's that term in which doesn't include x or the variable. Okay? Then we have linear equations. The variables of the linear equation could be written the variables of a linear equation could be written in a one-dimensional array. Okay? Matrices are arrays. Okay? Here, x is denoted as the set of all variables of the linear equation. In the linear equation, we had x1, x2, up to xn variables. And here, you could either write down in this way, x1, x2, up to xn. It's as a column. This is a column vector. Okay? It is a column vector. And here, x1 up to xn, this is a row vector. The horizontal one is called a row vector, and the vertical one is a column vector. And here, this sign, this symbol means transpose. This T, this capital T, is transpose. So the transpose of this horizontal vector is a vertical vector. So it becomes this, the role of this T, change the array as a row vector to a column vector. Okay? And change this to x1, x2, up to xn. As you see, it changed the vector to this form. It's transpose. It changed the row to column, or column to row. For the linear equation, if we replace x1 by s1 and x2 by s2 and xn by sn, these values that we give to the variables is going to be our solution. Okay? It's going to be the solution for our equation, for our linear equation. Here, if we replace each variable by a value and you get the same as the right-hand side, so we say s1, s2, up to sn. These values that we give to the x values, to the x variables, this gonna be the solution for the linear equation. And here you have some examples. It says, show that if x to be 1 and -2, here you have these two values, 1 and -2, is a solution for this equation. But this one is not. This one is not. Look, we need to show that 1 and -2 as a solution for this equation. Here, the first element is the value for x, for x1, and the second element is the value for x2. Here, we have x is 1 and -2 transpose, so it is 1 and -2. The above one is the value of x1 as value for the first variable in the equation. Okay, and the second value is the value of the second variable in the equation. That means this is x1 and this is x2. Let's check. If you replace x1 by 1 and x2 by -2, if you get 8, it means it's a solution for the equation. If not, it's not. Okay? How to check that 1 and -2 is a solution for this system, for this equation? We just replace x1 by 1 and x2 by -2. If you get 8, so it's the solution. If not, we say it's not a solution. Let's check. It's 2 times x1 is 1 minus 3 times x2 is -2. It must be 8. Let's check. 2 times 1 is 2. Minus 3 times -2 is plus 6. So 8 is equal to 8. That means it satisfies the equation. So 1 and -2 is a solution for the equation. 1 and -2 is a solution for the equation. And it says, show that 1 and 1 is not a solution for the equation. It's for the same equation, means for the same equation. Here, if we apply x1 by 1 and x2 by 1, both by 1, as you see, we have given this 1 and 1. So x1 is 1 and x2 is 1. We replace x1 by 1 and x2 by 1. And let's check if we get the same as the right hand side or not. Here we have 2 times x1 here is 1 plus, sorry, minus 3 times 1. Do you get 8 or not? 2, it's 2 minus 3 is 8. So minus 1 doesn't equal to 8. So it doesn't equal to 8. That means 1 and 1 is not a solution for that equation. 1 and 1 is not a solution for that equation. And that's okay. It's how to satisfy if a set of values is a solution for linear equation or not. Yeah, it's the solution for the above example. Here we have another example. It says determine whether either of the points is a solution to the given system of equations. If you have a system of equations and you have given a value for x1 and x2, these two values of x1 and x2, the values of x1 and x2 must satisfy all equations, then we say it's a solution for the system. If not, if it doesn't satisfy at least one of the equations, we say it's not a solution. Look, for the first point, for the first values of x and y, here, let's try -1 and -5. This is x value and that's y value. Okay? This is x and that's y. X is -1 and y is -5. Let's check if that point satisfies these two equations or not. It must satisfy both, then we say it's a solution. If not, we say no. So for the first equation, if you replace x by -1 and y by -5, here you have -5 is equal to 3 times -1 minus 2, which is -5. So these are equal. It satisfies the first equation. Let's check if it satisfies the second or not. Here, for the second one, we see y is -5 is equal to minus x, which is -1. We replace x by -1 and y by -5. -6. This equals to, the right hand side is 1 minus 6, which is -5. As you see, we got the same. Both sides are equal. -1 and -5 satisfies both equations. That means -1 and -5 is a solution for the system. It's a solution for the system. In the above example, we had only one equation. We said it's a solution for the equation. But for the systems, it must satisfy all equations. Then we say it is a solution for the system. And as you see here, -1 and -5 satisfy both equations. And we say -1 and -5 is a solution for this system. Okay? And let's try the second one. It's 0 and -2. 0 and -2. We have this point. Let's try that point for these equations. The first equation is y is 3x minus 2. And the second is y is -x minus 6. And the point is the point that we need to test if there's a solution for the system or not is 0 and -2. We try this point, 0 and -2 for this system. For the first equation, we replace here, this is x value and that's y value. You should know that if we have two values in a bracket, the first one is for x and the second is for y. Okay? If you have x and y as the variables, if you have x1 and x2, the first one is x1 and the second is x2. Here, we replace x by 0 and y by -2. Here, if we replace y by -2, this -2 is equal to 3 times 0 minus 2. And this equals to -2. As you see, it satisfies the first equation. Let's check if it satisfies the second or not. For the second equation, as we did before in the first equation, we replace x by 0 and y by -2. This -2 is equal to -0 minus 6. -6, here it's -x. X is 0, so it's 0. -2 is equal to -6. This doesn't equal. That means it doesn't satisfy the second equation. That means this point, 0 and -2, is not a solution for this system. It's not a solution for the system, but the above one is. Okay? Do you have any question? Okay, it's so easy. Then we have system of linear equations. If you have more than one linear equation and you want to solve them all together, it's called a system of linear equation. It could be more than two equations. Here, this is a linear equation. As you see, the exponent of all variables are 1. Even in the second equation, the exponent of all variables are 1. So it's also a linear equation. These two together is called a linear system. So if we have n equations, it's also called a linear system. Okay? Here we have m equations. These all together is called a linear system. It's called a linear system. If you have two or more linear equations, it's called a linear system. Here, for system, we have three types of solutions. We either have no solution, or exact solution, or infinite solution. We have these three types of solutions for a system. For a system, we have three types of solutions. We either have no solution or exact solution, it means one solution, or infinitely many solutions. Here, we say a system is called consistent if it has only one or more solutions. Okay, unique or infinite solutions. As I said, you have three types of solutions. We have no solution, listen, types of solutions. It's no solution, one solution, or unique solution, or infinite solution. We say if it has at least one solution, that means if it has either one solution or infinite solution, we say that system is called consistent. The system is called consistent if it has one solution or infinite solution. We have three cases for solutions. We either have no solution or one solution or infinite solution. That means if we have a solution for the system, if we have solutions for the system, we say it is consistent. If we have no solutions, we say it's inconsistent. Inconsistent. The system is inconsistent. Here we have unique solution. Infinite solution, that means we have more than one solution. For example, look, I think after this example, you'll have an example about that. No, yeah, that's it. Okay, I'll explain later. First, we have unique solution. Unique solution means we have only one solution. As we talk about linear systems, so the graph of a linear equation is a line, is it? It's a line. For example, if we have x plus y equals x, let's say 2. Okay? Here, let's say this, the equation. This is the graph of this linear equation. If we have another linear equation, let's say, so it's like this. It's like that. X plus y equals 2. So if we have y to be x plus 2, it's like this. Is it? It is for this one. As you see, these two equations intersect at only one point. If the lines intersect at only one point, means we have a unique solution. That means these two equations are common at only one point, which is this one. These two lines are common at only this. I mean, they have common at that point. Okay? At only that point, these two lines intersect each other. So this point is the solution for the system. It is a solution for the system. The system consists of these two equations. These two equations together is a system, and the solution for that system is that point, x coordinate and y coordinate of that. Yes, it's -1 and 2. -1 and 2. This point. So this point is the solution for that system. And here we have another example in the handout. Here we say that this system 1x plus 1y equals 4 and 2x minus 3y is 6. This system has a unique solution. So it means it has only one solution. As you see, the graph of these two equations, the graph of this and that one, intersect at this point. The graph of these two lines intersect at that point, and that point is x coordinate is 3.6 and y coordinate is 0.4. That means 3.6 and 0.4 is a solution for what? For the system. It is the solution for the system, and you have no any more solution. You have only that solution. So this solution is a unique solution. Okay, this solution is a unique solution. So if they intersect at only one point, we say it has the system has a unique solution. So if they intersect at more than one point, here for this one, we say this system has a solution at x1 to be 2 and x2 to be 3, and just check this. Replace x1 and x2 by these two values. It must satisfy both equations. Okay. Then we have infinitely many solutions. If we have infinite solutions, here we say 1x plus 1y equals 4, and also 2x plus 2y equals 8. As you see, the graph of these two lines are on each other. Okay, look, the graph of the first equation, 1x plus 1y equals 4. The graph is this line. This is the graph of that equation. And the graph of 2x plus 2y equals 8 is at the same line. It's also here. In how many points these two lines intersect? Infinite. Okay, so that's why we say it has infinite solution. It has infinite solution. So here, for this system, we have infinite solution. In other words, if we say, if we subtract one of them from the other one, let's say here, if we multiply the first one by 2 and subtract the second from the first, we get 0 equals 0, is it? 0 equals 0. In this case, if we get 0 in both sides, if we subtract one of them from the other one, if we get 0 in both sides, we say it has infinite solution. Try to remove one of the variables by subtracting one of them from the other one. Let's check if we want to remove x. We need to multiply this by 2 to have the same coefficients. Then we subtract one of them from the other one. We get x cancel out. Once we cancel out x, y is also. And the right hand side also, we get 0 equals to 0. So We say the system has infinitely many solutions. Even in this case, you say it's consistent. If we have one solution or infinite solution, you say the system is consistent. But if we have no solution, you say the system is inconsistent. And this is another example about that. Then we have another type of solution, which is no solution. If the lines are parallel and doesn't intersect each other, it means there is no any common point for those two lines. So the lines are parallel and we have no intersection point for those two lines, and we say the lines are parallel and have no solution. Okay, the system has no solution in this case if the lines are parallel. As you see, these two lines doesn't intersect each other. So these two lines together has no solution, and it's a system. These two lines together is a system. So the system has no solution. And we say the system is inconsistent. As you see here, this system has no solution. Okay? We say this system has no solution. Why? If we subtract one of them from the other one, if we get some impossibilities, we say it has no solution. For example, if we get 0 equals to 10, it's impossible. Okay? As you see, if we subtract the second from the first, these will cancel out. And these also. On the right-hand side, we get, in the left, you get 0. In the right, you get -2. Is it possible? No. So here, we say it has no solution. If you get some impossibilities, you say it has no solution. But if you get 0 for both sides, you say it has infinitely many solutions. Okay? And you say this system is inconsistent. Then we have matrices. In matrices, we have two dimensions. Rows, which are the horizontal ones, and columns, the vertical ones. If you have A to B, if you have, let's say, these four line of numbers, okay? The rows and columns are numbers of variables in which arranged horizontally and vertically. For the rows are the horizontal ones. These are these horizontal lines. If you have numbers here, let's say 2, 3, 2. And this is a row. And if you have 5, 6, 7, it's another row. And it could be 0, 0, 0, -2. It could be negative, it could be positive, it could be 0. Okay? And here's 0, 0, 0, let's see. Okay? We have this matrix. In this matrix, how many rows do you have? 4. We have 4 rows. The number of rows are the number of horizontal lines. And how many columns do we have? Look at the vertical ones. 1, 2, 3. We have 3 columns. So the size of this matrix is, first we count the rows, then columns. Rows are 4 by number of columns 3. So it's 4 by 3. The matrix is 4 by 3. This 4 by 3 is the size of the given matrix. Always the first one is the number of rows and the second is number of columns. And we usually use capital letters for matrices, okay? We use capital letters for matrices, A, B, C, and so on. Here you have these matrices. Look, A equals to this. This is a matrix. How many rows do you have? 2. And columns? So it's 2 by 3. And the second one is, how many rows do you have? 2. We have 2 rows. And how many columns? 1. So it's 2 by 1. If we have n by 1, if it's 2 by 1, 3 by 1, 4 by 1, n by 1. It's called a column vector. It's called a column vector. As you see, it is only one column. And if it is in this shape, it's called a row vector. Okay? How many rows do you have? 1. And columns? 3. If it's 1 by 2, 1 by 3, 1 by 4, 1 by n. Okay? This is called a row vector. But if it's a column, we say it is a column vector, and for the row is a row vector. And how about this one? It is 3 by 3. If the number of rows equal to the number of columns, we say that matrix is square. It's square, yeah. It's a square matrix. If the number of rows equal to the number of columns, we say the matrix is a square matrix. Here, G is a square matrix, but the others are not. Yeah, that's what we talked about before. Size of matrices, rows, and columns. We talked about these. And these are the size of matrices. We talked about these also. This is what we talked about in the previous slide. We said if it's 1 by n, it is a row matrix. It is a row matrix. It is in this form. It's 1 by n. If it's n by 1 or n by 1, it is on this form, and it's called a column matrix or a column vector. But if we have the same number of rows and columns, it's a square matrix. It is a square matrix. This is a column matrix, it's a row matrix, and this is square matrix. Then we have determinants. Determinants bakudaki snudari piyala. Snudari riskrao. Here, we first start with a 2 by 2 matrix and then 4 3 by 2 matrix. Okay. For finding the determinant of a matrix, the matrix must be square. If it's not square, we cannot find. Okay. As I said, the matrix must be square, then we can find the determinant. First, we talk about a 2 by 2 matrix, then for a 3 by 3 matrix. We just talk about 2 by 2 and 3 by 3 matrices for finding their determinant. As I said, the matrix must be square, then we can find this determinant. For non-square matrices, we have no determinants. Okay, and here you just take the determinants for 2 by 2 and 3 by 3 matrices. For 4 by 4 and others, you don't take it. Okay. For 2 by 2, it's so easy. Here, if we have a matrix A to be this matrix, it's a 2 by 2 matrix. As you see, we have 2 rows and 2 columns. It's a square matrix. To find the determinant of A, which is denoted by A in 2 vertical lines. Okay, this is determinant of A. It is the multiplication of these two, which is AD, then minus multiplication of these two, okay, CB. This is how to find the determinant of a 2 by 2 matrix. That's easy. Let's check and let's take an example. If A to be 2 minus 2, 3, let's say 4. How about this? What's the determinant of A? Is what? 2 times 4 minus 3 times negative 2. This equals to 8 minus 3 times negative 2 is negative 6, which is 8 plus 6 and is 14. This is the determinant of matrix A. That's how to find a determinant for a 2 by 2 matrix. It's so easy. And for a 1 by 1 matrix, it's easy. If A to be, let's say, 2, it's a 1 by 1 matrix. We have one row, one column. It is 2 itself. Okay, as the number itself. So the determinant of A is still 2. So if we have A to be negative 5, the determinant of A is still negative 5. That's the element itself. That's how to find the determinant of a 1 by 1 or 2 by 2 matrices. Here we have this example. The determinant of this matrix is 2 times 4 minus 5 times 1. Okay. That's it. That is 8 minus 5, which is 3. You can say determinant of A or det of A. Det A or this one, both are the same. Both mean determinant of matrix A. Do you need to solve any other example for 2 by 2 matrices? It's so easy. Before, okay, let's talk about it. Some matrices, then we take a break. For submatrices, we can take submatrices from a bigger matrix by removing rows or columns from the bigger one. For example, in this matrix, this is a matrix. Let me write down all the numbers here. This is 3, this is 1, this is 2. We have this matrix, okay? By removing a row or a column, or a row and a column from this matrix, we get another matrix. And the outcome is submatrix. It's called submatrix. Look, here, by removing this row and this column, what's left here? We get only these 4 elements. And these 4 elements are called submatrix. So it is 4, 7, 6, 9. This is a submatrix of this matrix. This is a submatrix of matrix A. We could get this one from matrix A. So it is a submatrix of matrix A. And how to name this submatrix? Look, we removed row 1 and column 2, is it? We removed row 1 and column 2. This is the first row. This is row 1, this is row 2, and this is row 3. And for the columns, it's column 1, it's column 2, and this is column 3. Which row and which column do we remove? We removed the first row and the second column. That means to name this submatrix, if you want to name it, we said A, we just subscript the number, the row number and the column number that you removed. Okay, which row did we remove? Row 1. Which column? 2. This equals to that. It's how to name a submatrix. Okay, okay. Let's check and let's take another one. F, this first, it's 2, it's 1, it's 3. So what if we remove, what if you remove this row and this column? What's left here? We get a 2 by 2 matrix. We already had A is a 3 by 3 matrix. If you remove a row and remove a column, so the number of rows and columns are reduced by 1. So we get a submatrix of it, which is a 2 by 2 matrix. The submatrix is what? Who's gonna tell me? 1, 2, then 4, 5. We have this submatrix. How to name it? What's the name of this matrix? A, first rows. You must first write down the row number and then column number. A33. How about if you remove this column and this row? What's left? 2, 3, 8, 9. What's the name of this submatrix? A, 2, 1. That's how to check submatrix and how to name them. So it's enough for now. Let's take a break. Here in the previous slide, we talked about how to find the determinant of a 2 by 2 matrix. How about finding the determinant of a 3 by 3 or 4 by 4 matrix? But here we just talk about a 3 by 3 matrix, not 4 by 4. Okay. For finding the determinant of a 3 by 3 matrix, which is for a square matrix, which size is 3. Here we say it is so determinant of A to be a 3 by 3 matrix, or let's say n by n matrix. It is A11. A11 is the element. Here, this one, this element is little a11 because it is the element of the first row and the first column. How about this one? It is A, first row, second column. Then this one, A13. This one, A21, A22, A23, A31, A32, A33. That's all. That's how to find these elements. Okay, it's the name of those elements. And what is A11? Capital A11. Here, it's a submatrix by removing the first row and the first column from matrix A. Okay? We say the determinant of an n by n matrix, it's A11 times determinant of A1 plus, sorry, minus A12 times determinant of A12 up to A1n times determinant of A1n. Here you can just take one row or one column. One row and one column. What we do here, let me write down a 3 by 3 matrix here and apply this rule. Here, if we have a 3 by 3 matrix, let's say 1, 3, 2, 2, 1, negative 1, 0, 2, 1. Let's say 0. Here, what we take? If you take the first row, or second row, or third row, or first, second, or third column, you are free to take any of these. Okay? And you can just take one of them. If you take the first row, to find the determinant of A, what we do? If we work on the first row, for the first row, this is the first row. We remove the first row, and then we remove the first column, and then second column, and then third column. Okay, these all are on the first row. Okay, here in finding the determinants and cofactor, we must show a row and a column. It's not enough to delete or remove only one row or only one column. We must remove a row and a column also. Look, as I said, we are going to work on the first row. On the first row, we have 3 elements. This is A11. The second is A12. And the last one is A13. Okay? What we do for finding the determinant of A, look, it's A11. The first one is positive. It's always positive, the first element. What's in the top left corner, it's always positive. Its coefficient is positive. Then the second one is negative. The third one is positive, then negative, positive, then it's and so on. Here, for finding the determinant of matrix A, what we do? We say it is determinant A is A11 times determinant of capital A11. What's capital A11? It's a submatrix from matrix A by removing the first row and the first column. That's it. Then plus. Look, it's negative, so we must give a negative sign to it, not plus. Minus A12 times determinant of what? Capital A12. Okay? Capital A12. Then plus. The third one is plus. A13. Look. We took the first row. A13 multiplying by determinant of submatrix of A13. As for someone, if he or she take the first row to work on for finding the determinant. So what if someone take this row? Or what if someone take this column? It's possible. At all cases, you must get the same result. At all cases, you must get the same result. Look, if someone take this column, okay, what are the elements on that column? It is A1, 2, A2, 2, A3, 2. How to give these positive and negative signs? Look, what we do. We say the coefficient is -1 to the power row number plus column number. What's this row number and column number? 1 and 2 is 3, is it? It's 1 plus 2. Okay, look. This is 1, 2. Is it? It's 1 plus 2, which is 3. Since it's odd, so it's -1. Okay? If it's odd, it's -1. If it's even, it is 1. اگر تاج بو سالب كات ناقص زي بتوين شمالي سالب بتوين شمالي تاج سالب ناقصه اگر موجب بو بعدين اگر جود بو موجب. Look, if you take that column, we say it is -A12. Why negative? Because it is the first row and second column was 1 plus 2. -1 to the power 1 plus 2 is negative. So the determinant of A is -1, 2, A12 times the determinant of what? A12. The same. Then this one, A22, is it positive or negative? Its coefficient. It's positive because 2 plus 2 is positive, is even, so it's positive. Then plus A22 times determinant of A22. Then this one is positive or negative? Negative. It's minus A32. Determinant of A32. It's for someone if he or she take the second column. Which one is the easiest one? Which column or row, which row or which column is the easiest one to work on? Third row. Yes. Why? Yes. Take the one which includes the most number of zeros. Okay, it's easy because here it is A31 is 0, A33 is 0. So you just don't need to calculate these two terms. You just calculate one term, which is A32. Okay. Now here we have. That's all what we talked about. As you see, it's 1, 1, it's 1, 2, it's 1, 3, it's 1, 4. It is up to 8. Okay. Here, 1 plus 4 is odd, so it's negative. It's positive, negative, positive. It's like that. That's all what we talked about here. And this is the rule for finding the determinant of a 3 by 3 matrix. Here, it takes the first row. You can take the second row, the third row, and even any of the columns. Look at this example. It says use a cofactor expression across the third row to compute determinant of A. Okay, now this method is called cofactor method. It's called cofactor method. Let's find it. Let's find the determinant of this matrix. Which row or column should we take? The easiest. You can take the third row. How about the third column? It's the same because both includes 2 zeros. You can also take the first row, even the second row, and the first and second column. Any of these you can take. And you must get the same result. At all cases, you must get the same result. So it's true if you take any of the rows or columns. But the easiest one is the one which includes the most number of zeros. Okay? Let's try this. To find the determinant of this matrix, let's take the third row. Okay? Or the third column. No problem. If we take the third row, in the third row, we have 3 elements. What are the elements? It's A, 3, 1. This is A, 3, 2. This A, 3, 3. What's the coefficient of this one? Is it positive or negative? It's positive because 3 plus 1 is 4. So it's positive. And this one is negative. This one is positive. So it's negative and that's positive. These are the coefficients, the sign of coefficients. That means the determinant of A is what? Determinant of A is A31, little A31, times determinant of capital A31, then plus. So it's minus A32 times determinant of capital A32. For the last one, it's plus A33 times determinant of A33. Here, we need to find the submatrices capital A11, capital A31, A32, and A33. We need to find these 3 submatrices. I mean this, and this. We need to find these 3 and then finding their determinants. But before we do that, replace little A31, little A32, and little A33. Okay? And then find capital ones. Okay? What's little A31? 0. So the determinant of A, determinant of A is 0 times determinant of A31. So it's 0. We don't need to find determinant of A31. We can save time. Okay? Then minus A32 is negative 2. And you already have a negative sign, it becomes 2, is it? Plus 2 times determinant of A32. Then plus A33 is 0 times determinant of A33. So it's 0. This is also 0. So you don't need to find capital A31 and capital A33. Okay? We don't need to find these 2. This and this are 0. So we don't need to find capital A31 and capital A33. We don't need to find these 2 because the term is 0. So what do you need to find? Only A32. Only A32. We just need to find the determinant of that submatrix. So you can save time if you first replace little a's. Okay. Now, what's A32? A32 is this. This A32. What's A32? Is 1, 2, 0, negative 1, is it? What's the determinant of this 2 by 2 matrix? As you see, we could reduce the 3 by 3 matrix to a 2 by 2 matrix. And we have a rule for finding determinant of a 2 by 2 matrix. What's the rule for finding this determinant? Here we multiply these two minus, we multiply these two. That's all. As 1 times -1 is -1, minus 2 times 0 is 0. It is -1. So this is the determinant of A3, 2. Now we replace this by -1, and the result is 2 times -1. As you see, as we said, these two terms are 0. So you just have this term. Let me write down 0 for those two terms. 0 plus 2 times -1 plus 0. The first and third terms are 0 because the entries of those two elements are 0. And this equals to -2. So the determinant of this matrix is -2. It is -2. Now, what if someone take another row or another column? You must get -2 if you take any of the rows or columns. Let's try. Okay? Let's try another row or column. Which one should we take? Just choose a row or column. Tell me. Which one? First row. Okay. Let's take the first row. In the first row, we have 3 entries. A11, A12, A13. Okay? And the determinant here is, we said it, is A11 is positive, is it? But 1 plus 1 is positive, is 2. So it's positive. A11 determinant of capital A11. Then plus. A12 is plus or minus? It's minus. A12 a determinant of A12. Then plus. A13 determinant of A13. Now we first replace the little A11, A12, and A13, and then we try to find the submatrices. Okay? Let's replace A11, A12, and A13, which are these 3 values. Okay? This equals to A11 is 1. So we don't need to write down it. It is still determinant of A11. Then minus. A12 is 5. It's 5 times determinant of A12. And A13 is 0. So you don't need to write down that here. Okay? It's plus 0. We don't need to write down this. That's it. Now, how many submatrices should we find? 2, which are A11 and A12. Let's find them. A11, we can get it by removing the first row and first column, as it is 1, 1. So you remove first row and first column to get A11. And this A11 is 4, -1, -2, and 0. How to find the determinant of this matrix? We need its determinant. Multiplying these two minus multiplying these two. At 0, multiplying 4 times 0 is still 0. And -2 times -1 is minus. And -2 times -1 is 2. So it is -2. Okay? It is -2. Now we say A11 is -2. So its determinant is -2. -2. Then minus. Sorry? Yeah, and we have a negative sign for the row. Okay, so that's how you get negative. Now we have minus 5, determinant of A12. What's A12? A12 is this submatrix by removing the first row and second column. What's A12? Is 2, 0, negative 1, 0. That's 0. That's it? Look, indeterminants, if a row or a column, if all entries of a row or a column is 0, the determinant is 0. So if this is 0, so the determinant is 0 at all. Okay? If a row, if the elements of a row is 0, or if all elements of a column is 0, we say the determinant is 0. It's just like just for you. Here, a determinant of A12 is 0. We found it. It's 0. What we get? Minus 2. And here we got the same. Minus 2. Even if you take any other row or any other column, you must get the same result. Yeah, that's the example. Okay, it's enough for now. Let's take a break. After the break, we'll continue to finish matrix inverse. Okay. Today we talked about matrices and also the determinant of matrices for a 2x2 matrix and a 3x3 matrix. Okay. We now have inverse matrix or matrix inverse. Here we talk about how to find the inverse of a matrix. It's important to know how to find the cofactor for the matrix. The cofactor is the list of all submatrices as we did before, as we found before. Okay? So if you know how to find the submatrices, so it's the cofactors. These all elements, put them all together in a matrix, is going to be the cofactor matrix. Okay? If you know that, it's easy to find it is inverse. We say, if you have two matrices, let's say A and B. As it's written here, we say the matrix C is called as inverse of A if their multiplication is an identity matrix. Let me tell you what's an identity matrix. An identity matrix, for example, if we have I2 means an identity matrix of the size of 2 by 2. Identity matrix is always a square matrix. This subscript is the size of the matrix. It's 2. That means it's a 2 by 2 matrix. So it is 1, 0, 0, 1. In a matrix, we have two diagonals. We have the main diagonal and the second diagonal. We have two diagonals. As you see, if you have this matrix, it's A, maybe MSC, D, E, F, G, H, I. Okay. If you have this matrix, in this matrix, as I said, you have two diagonals. This diagonal is called the main diagonal. This is the main diagonal. And the second diagonal is this. These elements are called the second diagonal. Second diagonal. This is called the second diagonal. We say if all the upper elements and lower elements of the main diagonal are 0, and the entries of the main diagonal are all ones, we say that matrix is called an identity matrix, like this one. This is an identity matrix. First, just select the main diagonal. The upper elements of the main diagonal are 0, and the lower elements are also 0, and the elements on the main diagonal are all ones. This. So this matrix is called an identity matrix. Let's take another one. If we have I3, the elements on the main diagonal are all 1, and all the other elements must be 0. All the other elements must be 0. All the upper and lower elements must be 0, 0, 0, 0, 0, 0, 0. This matrix is called an identity matrix of size 3. As you see, the size is written here. And the multiplication of an identity matrix with any matrix is the matrix itself. It's identity. So if you multiply it by any matrix, it's the matrix itself. Okay? And here we say for inverse, we say C is called the inverse of A. C is called inverse of A. If C multiplying by A to be an identity matrix, or A times C is an identity matrix. If the multiplication of two matrices is an identity matrix, that means these two matrices are inverse to each other. It means those two matrices are inverse to each other. Here we say C is the inverse of A if their multiplication is an identity matrix. Or you can say A is an inverse of C if their multiplication is an identity matrix. Okay, so you know what's an identity matrix? It is I2, and this is I3, and therefore I4, so okay. Here, for finding the inverse of matrix, as I said before, we just work on 2 by 2 and 3 by 3 matrices. Okay, for finding the inverse of a 2 by 2 matrix, what we do? We need to have the determinant. We say the inverse of a matrix could be found if the determinant of the matrix is not 0. If the determinant of a matrix is 0, we say the inverse doesn't exist. Okay? We say if A to be this matrix and the determinant of matrix A, multiplication of these two minus multiplication of these two, is the determinant. We say if the determinant doesn't equal to 0, then we can find its inverse. If it equals to 0, we say it doesn't exist. The inverse doesn't exist. Okay? So the inverse of matrix exists if its determinant is not 0. If it is not 0. If the determinant of the matrix is not 0. For a 2 by 2 matrix, what we do? If we have this matrix A, B, C, D. If this is matrix A. To find the inverse of matrix A, and it's denoted by A to the power -1. This means inverse of matrix A. We say A inverse is what? It's 1 over determinant of A. This is matrix A. 1 over determinant of A times what we do on matrix A. We say it is for a 2 by 2 matrix. What we do? It's different. We find adjoint for matrix A. For a 2 by 2 matrix, it's fixed. It's a rule. You can directly write down the adjoint. What we do? We exchange or we interchange these two. We interchange these two. If we interchange these two, what we get? We get D here and A here. And we change the sign of these two. We just change their sign. If it's negative, if they are negative, we make them positive. And if they are positive, we make them negative. Okay? We just change their sign. This is minus C, minus B. As you see, we interchange these two without changing their sign. And we change the sign of these two. Okay? That's all that we do on the matrix A. Then we say 1 over determinant multiplying by this matrix D minus B minus C A. Calculate this and then you get the inverse of the matrix. Just calculate this and you'll get the inverse of the matrix of any 2 by 2 matrix. Okay, here inverse of a matrix is a matrix in the same size of the given matrix. Here we can find inverse of matrix if it's square. It must be square because here we need to find its determinant, and we already talked about determinant that the matrix must be square, then we can find its determinant. So the matrix must be square and the determinant must not be 0. The determinant must not be 0. Then we say the inverse of the matrix of the given matrix is a matrix in the same size as the given matrix. As you see here, we have a 2 by 2 matrix. So its inverse is a 2 by 2 matrix. For a 3 by 3 matrix, the inverse is a 3 by 3 matrix, and so on. Okay? We use this rule for finding the inverse of any 2 by 2 matrix. Let's take a matrix. Okay? Let's say A. I think there's an example here. Yeah, we have this. This matrix A. To find the inverse of this matrix, what we do? Let's first write down the rule. In the rule, we need to have determinants, and we also need to interchange these two and change the sign of these two. Okay? We multiply 1 over determinant by this matrix that you get here by interchanging those two elements and changing the sign of those two elements. The multiplication of those two, we get the inverse. So A inverse is asking about finding A inverse. A inverse is 1 over determinant of A by what? Interchanging these two. Okay, this is 2, 4, and change the sign of these two. Minus 3, minus 1. We don't change their places. We just change their sign. Okay? What if this was negative? This would be positive and this is negative. Okay? So now we need to find the determinant of the matrix. It's enough to find the determinant, then multiplying them. What's the determinant of this matrix? We said it's multiplying these two minus multiplying these two. It's for any 2 by 2 matrix. You can get the determinant but by just multiplying these two minus multiplying these two. That's all to find the determinant of any 2 by 2 matrix. So det A, which the determinant of A is, multiplying these two, which is 8, minus multiplying these two, which is 3 and 5. This is the determinant of matrix A. This is the determinant of matrix A. Now, we just multiply this matrix by 1 over 5. That's all. I'm just going to delete this determinant that you found. This is 5. So we get 1 over 5. So A inverse is 1 over 5 multiplying by 2, negative 1, negative 3, 4. Now we multiply each element by 1 over 5. Or we can say divide each element by 5. Okay? We divide all the elements here by 5. Or multiplying all by 1 over 5. This equals to 2 over 5. 2 over 5. Then negative 1 over 5. And also we have minus 3 over 5 and 4 over 5. This is the inverse of this matrix. It is the inverse of the given matrix. Okay? Do you have any question? It's so easy for 2 by 2, it's so easy. Now, we work on finding the inverse of a 3 by 3 matrix. Okay? If you just know this rule, it's easy. 1 over determinant, then interchange these two and change the sign of those two. That's all. It is how to find the inverse of that matrix. Then, to satisfy, if you multiply this matrix by the given matrix, we get this matrix. This matrix A. And this is A inverse. Multiplying them, we must get an identity matrix. You don't need to do this, okay? And just for satisfying, as you see here, we got an identity matrix. So this is the inverse of that matrix, and even this is inverse of that matrix. Any of them is the inverse for the other one. Then for 3 by 3 matrix, for finding a 3 by 3 matrix inverse, what we do, we use the same rule. We use the same rule. We say A inverse is 1 over which one? Which one is minus?
Like negative 1.
Okay, let me tell. I know what.
Now consider the
نعم إكسانية بس في السيف كان لقداني أمدو ماتريكس أكاتا أما باشا أما إنفيرسا كي تواب إنفيرسا بوتمان لقداني هر ماتريكسك لإنفيرسا كي أكاتا شي أكاتا أيدنتي ماتريكسك أما ماتريكسا كي أما إنفيرسا كي لقداني هر دويان كدية شي أيدنتي ماتريكس أما كهمانة شيا I2. Okay. Then for a 3 by 3 matrix, to find the inverse, what we do, we say A inverse, if A to be a 3 by 3 matrix, so its inverse must be a 3 by 3 matrix also. Okay. For any size of square matrix, the inverse must be in the same size. As you see in the previous example, the matrix A is a 2 by 2 matrix. How about its inverse? It's also a 2 by 2 matrix. What if this 3 by 3 matrix? So its inverse must be 3 by 3 matrix. Okay. We say A inverse is 1 over determinant of A. We already studied that, how to find the determinant of a 3 by 3 matrix. We could take any row or column and work on it to find the determinant. Okay? Multiplying by adjoint of A. Now I'm going to tell you what's adjoint of A. How to find adjoint of a matrix. Okay? We say adjoint of a matrix is the transpose of the cofactor matrix. Is the transpose of the cofactor matrix. It's cofactor matrix. Transpose is adjoint. First, let me tell you what's transpose, and then I'll tell you how to find the cofactor matrix. Look, for finding the transpose of a matrix, we just interchange rows and columns. First row becomes the first column. Second row becomes second column. Third row becomes third column. That's all. Look, if A, let's take a 2 by 2 matrix. 2, 3, minus 5, oh. What's the transpose of A? As I said, the first row becomes the first column. It's 2 and 3. This is the first row there. And it becomes the first row, the first column. And the second row becomes the second column. It's minus 5 and 0. This is the transpose of A. That's how to find transpose of matrix. Then, if let's we have another example. 2, 3, 5, negative 2, 7, 6. If you have this, how to find its transpose? Here, B transpose. How many rows do you have? 2. So the first row becomes the first column. So it becomes 2, 3, 5. And the second row becomes the second row column. Minus 4, 7, 6. Do you have any more rows? No. So this the transpose. As you see, in transpose of matrix, we just interchange rows and columns. So the number of rows become the number of columns. And also, the number of columns become the number of rows. As you see, this is 2 by 3. And its transpose is 3 by 2. As you see, you just interchange the number of rows and columns. Okay, that's it. For a 3 by 3 is also it's the same. We just interchange, or we just change the first row to first column, second row to second column, and the third row to third column, and that's all. It's how to find the transpose of a matrix. Here, we need to find the transpose of the cofactor matrix. Then, let's see how to find cofactor of the matrix. So here, we already studied that, how to find determinant, and we just talked about how to find the transpose. So what else should we know? The cofactor matrix. Now we talk about how to find the cofactor. If you know that, so it's easy, it's just calculations, nothing else. Look, here it's for determinant. You just take either a row or a column and work on it to find determinant. Do you need to solve this, or it's clear? We talked about this type of examples. Actually, we solved some example about how to find the determinant of a 3 by 3 matrix. If you remember, we took the third row and the first column also. In both cases, we got -2. Okay.
Yeah.
So do you need to do this? So it's easy. This is how to find the determinant of matrix. Then, for finding the cofactor matrix, this is matrix A. Here in this example, it says find the inverse of this matrix. To find the inverse, let's first write down the rule and check what do we need to find to calculate. We say A inverse is 1 over determinant of A multiplying by cofactor or adjoint of matrix A. Okay? And the adjoint is the cofactor matrix transpose. This all is adjoint of A. Okay? For finding adjoint, we need to find the cofactor and then take its transpose. Now, we need to find the determinant of the matrix A and also cofactor matrix of A. And then find its transpose. And then finding its transpose. We need to find determinant of the matrix. Determinant of the matrix here, you can take either this row or this column, this, or this, or that one, any of them. You can take any of the rows or columns and work on it to find its determinant. We already studied that and solved some examples about that. I'm not going to talk about this again. And it is -2. The determinant is -2. And if you take any other row or columns, you must take -2. You must get -2. So the determinant of this matrix is -2. Now, to find the cofactor, we need to find the cofactor. After finding the cofactor, what we do? We find its transpose. I multiply it by 1 over the determinant. That's all. Here, to find the cofactor, let me do it here. I'm going to work on it here. The cofactor matrix of A is what? It is submatrices with their sign. Okay? This one is negative, then positive, then negative. Because it is 1, 1, it's 1, 2, it's 1, 3. So it's positive, negative, positive. Positive, negative, positive. Is it? Then, for this one, 2, 1, 2, 2, 2, 3. The sign of this element is negative. This one is positive. This is negative. Okay? Then, 3, 1, 3, 2, 3, 3. This is positive, negative, positive. You should know these signs. And also, you can start from positive. Start from positive, then negative, positive, negative, positive, negative, positive, negative, positive. Okay? That's all. Now, what should you find? We need to find the submatrices. All submatrices of A. All submatrices of A. Here we can get A11. Is it? We can get capital A11. What's capital A11? It's this. Is it? Determinant of this one. Determinant of this matrix. It's determinant. I'm just give a determinant to it. Then here, let me do it here. Look, we say C C11 is the determinant of A11. Okay, with its sign, it's -1 to the power 1 plus 1. Determinant of A11. Its sign with the determinant. And C12 is what? It is -1 to the power 1 plus 2. And determinant of what? A12. What's A12? We remove first row and second column. As you see, it's first row and second column. We remove these two, we get this matrix. We find its determinant. I'm multiplying by -1 because the exponent is odd. Then C13. From this one, we get C11. C12, C13. C13 is -1 to the power 1 plus 3. Determinant of what? A13. Okay? As for these three, how about here? What we get? C21. It is -1 to the power 2 plus 1. Determinant of what? A21. And here is C what? C22 is -1 to the power 2 plus 2. Determinant of A22. And so on for these four also. Okay, we find these all. Then we say the cofactor is C11, C12, C13. Then C21, C22, C23, and C31, C32, and C33. Let's find them. What is C11? Let's start from C11. What's C11? Here, it's -1 to the power 1 plus 1. This is 1. It's positive, is it? Then, how to get determinant of A11? What's A11? A11 is a submatrix by removing the first row and the first column. The first row and the first column. So what's left? This one. We find its determinant. So it is determinant of what? -1, -1, 2, 1. This is A11. Okay? What's this determinant? Multiplying these two minus multiplying these two. This equals to -1 minus multiplying these two is -2. And the result is 1. So it is 1. This is 1. What's this? It is C11. It is C11. We replace this by 1. And then we find C12. What's C12? We can find all here. Look, -1 to the power 1 plus 2 is -1. So it's minus. Determinant of what? We remove the first row and the second column. If you remove the first row and the second column, what's left? -3, -1, 5, 1. Determinant of this matrix is multiplying these two minus multiplying these two. But be careful, here we have a negative sign. It's minus. The determinant is -3 times 1 is -3 minus 5 times -1 is -5. And it is -3 plus 5. It is -2 because the bracket is 2 and we have a negative sign. which is -2. And C12 is -2. C12 is -2. Then we find C13. Let's find C13. So it takes time, but it's easy. C13 is -1 to the power 1 plus 3, determinant of A13. What's the sign here? It's positive. So this becomes 1. And this equals to determinant of what? A13. We find this submatrix by removing the first row and the third column. The first row and the third column. We get -3, -1, 5, 2. We multiply these two, we find this determinant. Multiplying these two is -6, minus. Multiplying these two is -5. And we get -6 plus 5, which is -1. And C13 is -1. Then we find C21, C22, C23, and so on. Okay, we find these all. Let's find C21. What's C21 here? C21 is what? This one is. It's -1 to the power 2 plus 1, which is negative, times determinant of what? A21. This becomes negative, minus determinant of what? A21. We remove these two rows and columns. We get 1, 2, 2, 1. And we get minus. Determinant of this matrix is multiplying these two minus multiplying these two, which is 1 minus 4. We get -3 and is 3. What's this? It is C21. So C21 is -3. Then for C22, you find them all. C22 is -1 to the power 2 plus 2, determinant of A22. So C22 is -1 to the power 2 plus 2 is 1, because its exponent is even. -1 to the power 4 is 1. This is 1. Then determinant of what? Of removing second row and second column. We get these two and these two elements. Okay? Get 2, 2, 5, 1. Then it is multiplying these two. The determinant of this matrix, of this 2 by 2 matrix, is 2 times 1, which is 2 minus. 5 times 2 is 10, which is -8. And this is -8. Then for C23, look, it's found here. That's all that we need to do. It is C23, it's 1. It's A23. And Cij is -1 to the power I plus j times this determinant, and we get 1 because it's negative. The sign is negative there. And this is the cofactor matrix. It is C31, C32, C33. This is the cofactor matrix. And we already found the determinant. This is the cofactor matrix. and we found the determinant. We say determinant is, I think it was -2. Let me check. Yes, it's -2. The determinant is -2. And the cofactor matrix is this one. What should we work on this? What should we do on this cofactor matrix? We need to find its transpose. We say A inverse is 1 over determinant of A times cofactor matrix transpose. Okay? We already found cofactor matrix and also the determinant. Determinant is -2 and cofactor matrix is this one. We find that the transpose of this matrix, then multiplying by 1 over the determinant. Let's find the transpose of this matrix. So its transpose is the transpose of this matrix, and it equals to what? Let's find. It is. The first row becomes the first column. It is 1, -2, -1. And the second row becomes the second column. It's 3, -8, 1. Then the third row becomes the third column. 1, -4, and 1. This is the transpose of the cofactor matrix. So this is that matrix. And determinant is -2. So we just multiply each element here by -1/2 or divide each element by -2 to get the inverse. And this equals to, let's write down here. A inverse is 1 over -2 multiplying by this matrix that you found, the transpose. This one is. Okay? The transpose of the cofactor matrix is the one which is here. Now we say it's 1, 3, 1, -2, -8, -4, -1, 1, 1. This equals to what? We just divide each element by -2. So the first element becomes, this becomes what? This becomes -1/2. And this element is -3/2. And this one is -1/2 because we divided by -2. Then this element is 1. That's positive 1. -2 divided by -2 is 1. -8 dividing by -2, it's 4. Then -4 dividing by -2 is 2. And the last row is 1/2, -1/2, and -1/2. This matrix is the inverse of the given matrix. This matrix is called the inverse of matrix A. Okay, it takes time, but it's easy. Okay, finding the cofactor matrix takes time, but it's easy. If you just know how to find only one element, all the others are the same. Okay, even if you know is C11, you should, and you also know how to find C12, C13, C22, and all the others. If you just know only one C, you can find all the others by using the same technique. So it is how to find the inverse of a matrix, of a 3x3 matrix. This one is the inverse. Okay, And here you have two exercises. So it's enough for today. I'm not going to talk about system of linear equations because I just want to talk about this all together because these relate to each other. Okay. It's enough for today. Let me check the attendance.